You're living in an era where artificial intelligence is transforming every aspect of our lives. Deep learning, a branch of AI, has enabled machines to see, hear, and even write with abilities that rival or surpass humans. From self-driving cars to AI-generated essays, the impact is everywhere. But for many, the breakthroughs in deep learning seem locked behind complex jargon and advanced mathematics. This video is your gateway to understanding the fundamentals of deep learning, breaking down the barriers so anyone with basic Python and calculus can grasp the essentials. Let's embark on this journey to demystify deep learning together. Deep learning is not just a buzzword. It's a driving force behind today's most impressive AI feats. Companies like Google, Microsoft, and Facebook are investing heavily in deep learning teams, pushing the boundaries of what machines can do. For the rest of us, understanding deep learning opens doors to new career opportunities and the chance to solve real-world problems. This video will help you build a strong intuition for deep learning, so you can join the conversation and even contribute to this rapidly evolving field. Journey through deep learning starts with building a solid mathematical foundation. It begins with linear algebra and probability, essential tools for understanding how deep learning works under the hood. Next, it explores the architecture of neural networks, how to implement them, and how to train and evaluate them using real-world data. Later, we dive into specialized applications like computer vision, sequence analysis, generative modeling, and interpretability. Each topic is broken down from first principles, making advanced concepts accessible and practical. Linear algebra is the backbone of deep learning. At its core, it's about manipulating matrices and vectors, structures that store and organize data. Imagine a spreadsheet, rows and columns of numbers representing features and data points. In deep learning, matrices represent datasets and neural network weights. Operations like addition, multiplication, and inversion are fundamental, enabling efficient computation and transformation of data. Understanding these basics is crucial before diving into more complex neural network operations. Matrix operations are at the heart of deep learning computations. You can add or subtract matrices of the same shape, multiply a matrix by a scalar, or perform matrix multiplication, which combines two matrices in a specific way. The identity matrix acts like the number 1 for matrices, and the concept of inversion is similar to finding a reciprocal. These operations allow us to transform data, solve equations, and build the mathematical framework that powers neural networks. Vectors are simply one-dimensional arrays of numbers, and they play a key role in deep learning. They can represent individual data points or weights in a model. Operations like the dot product and outer product help us measure similarity and build more complex structures. Orthogonality, or perpendicularity, between vectors is a powerful concept, especially when analyzing data in high-dimensional spaces. Mastering vector operations is essential for understanding how neural networks process and learn from data. Multiplying a matrix by a vector is a fundamental operation in neural networks. It allows us to apply transformations to data, such as combining features or applying learned weights. This operation is used repeatedly in neural networks to process inputs and propagate information through layers. Understanding matrix vector multiplication helps you see how data flows and changes as it moves through a neural network, setting the stage for more advanced concepts. Two important concepts in linear algebra are the column space and the null space of a matrix. The column space represents all possible outputs you can get by multiplying the matrix by different vectors, essentially, all the combinations of features. The null space, on the other hand, consists of all vectors that the matrix maps to 0. These spaces help us understand redundancy in data and are key to techniques like dimensionality reduction, which simplify complex datasets for more efficient learning. Eigenvectors and eigenvalues are special properties of matrices that reveal deep insights into data. An eigenvector remains in the same direction after a matrix transformation, only scaled by its eigenvalue. These concepts are crucial for algorithms like principal component analysis, PCA, which is widely used for reducing the dimensionality of data while preserving important patterns. Understanding eigenvectors and eigenvalues connects the theory of linear algebra with practical data science applications. Probability helps us quantify uncertainty in the world and is deeply intertwined with deep learning. Whether it's predicting the outcome of a coin toss or the likelihood of a neural network's classification, probability distributions are everywhere. Key concepts include sample spaces, events, and the rules that govern probabilities. Both frequentist and Bayesian perspectives offer ways to interpret and update our beliefs based on new data, which is essential for building intelligent systems. Conditional probability lets us update our beliefs when new information is available. For example, knowing the outcome of one event can change the likelihood of another. Independence means that two events do not affect each other's probabilities. These ideas are crucial in deep learning, especially in classification tasks where models predict the probability of different outcomes given specific inputs. Mastering conditional probability and independence is key to understanding how models learn from data. Random variables map outcomes to numbers, allowing us to summarize experiments and model uncertainty. Expectation gives us the average value we expect to see, while variance measures how much outcomes deviate from this average. These concepts are used throughout deep learning, from understanding dropout regularization to evaluating model predictions. Grasping expectation and variance helps you analyze and improve the performance of neural networks. Bayes' theorem is a powerful tool for updating probabilities based on new evidence. It's widely used in medical diagnosis, spam detection, and many areas of AI. In deep learning, Bayes' theorem helps us reason about model uncertainty and make better predictions. By understanding how to combine prior beliefs with new data, you can build models that adapt and improve as they learn. Entropy measures the uncertainty in a probability distribution. Cross-entropy and KL divergence are used to compare distributions, and they play a central role in training neural networks. For example, minimizing cross-entropy is equivalent to maximizing the likelihood that a model predicts the correct label. These concepts are not just theoretical, they are the backbone of loss functions that guide neural network learning. Not all data is discrete. Many real-world variables are continuous. Probability density functions, like the Gaussian distribution, help us model and reason about continuous data. The central limit theorem explains why Gaussian distributions appear so often in nature and data science. Integrating probability concepts with linear algebra gives us the tools to build and train powerful deep learning models that handle all types of data. Neural networks are inspired by the human brain, which excels at perception, memory, and learning. While traditional programs follow strict rules, neural networks learn from examples, just like we do as children. By adjusting their internal parameters based on feedback, neural networks become better at recognizing patterns, making predictions, and solving complex problems. This approach is at the heart of modern AI and deep learning. Traditional computer programs excel at arithmetic and following explicit instructions, but they struggle with tasks like handwriting recognition or speech comprehension. These problems are hard to solve with fixed rules because they require flexibility and learning from experience. Neural networks overcome these limitations by learning directly from data, enabling breakthroughs in areas where traditional programming falls short. Machine learning flips the script by letting computers learn from examples instead of explicit instructions. Just as children learn to recognize objects by seeing many examples, machine learning models improve as they are exposed to more data. By defining a model and a way to update its parameters based on feedback, we can train computers to solve complex tasks that were once thought impossible for machines. The core of machine learning is the idea of modeling, defining a function that maps inputs to outputs, and then optimizing its parameters to minimize errors. For example, predicting exam performance based on sleep and study hours can be modeled with a linear classifier. Optimization algorithms adjust the model's parameters to improve accuracy, allowing the model to learn from mistakes and get better over time. This process is the foundation of all deep learning systems.